Yeah, hi, I'm Drina, and I am in New Mexico, so next to Arizona.
Okay.
I teach eighth grade math. Um, is there anything else you want to know, or just
Well, I guess one thing is, so you teach eighth grade math, not high school.
uh-huh.
So what is the reason you're in the program? Just out of curiosity.
So I teach eighth grade math. I do teach Algebra 1. It's an honors class to eighth graders, and then I actually also teach at my community college.
Oh, okay.
So I am here so I can teach more classes at my community college.
Okay, yeah. Yeah, include that. I'm always interested in that. And
Uh-huh.
actually, I'm gonna ask you to fill out a little uh, form to tell me to sort of make this information in writing so I have it, because we like to
Sure.
keep track of who's taking this class and for what reasons. David, you're next.
Yeah. Hello, my name is David. I'm in Austin, Texas, and I'm currently a seventh grade math teacher.
Oh, also, so do you have a similar reason for wanting to take the grad classes?
Yes, I'm hoping to teach high school next year, and I
Okay.
do hope to teach at a community college as well. So more like dual credit courses.
Okay.
Yeah.
Okay. Good. Savannah, you're the next one I see.
Hi, I'm Savannah. I live in Phoenix, Arizona. I actually work full time for Grand Canyon University in the
Oh,
Colangelo College of Business. Um, so I taught math for 6 years, mostly middle school math, but AP Calculus and Pre-Calculus one of the years. Um, I miss teaching, but I'm not quite ready to jump back into it full time with two little kids. So I just am hoping to get some adjunct classes after I complete this program.
okay. At GCU.
We'll see. I know that Dr. Boldway kind of said that they are always in need of some of the lower level math classes, which is where I love teaching math intervention. So I'm like, yeah, I would be happy to kind of teach some of those. So we'll
Yeah.
see. But yeah, my
Yeah.
boss is willing to let me take on an adjunct course a semester with my full-time load. So
Okay. Yeah. I have a feeling they're going to need people next year. That's my feeling. Okay, Lacey.
Hi, I'm Lacey. I teach high school math, and right now, this year, I'm teaching geometry and algebra 2. I live in Washington, so I am an hour behind everyone, so it's 4 o'clock here.
Oh, okay. Is that good or bad for you? That's really
Um,
close to your school,
yes, I don't have time to drive home to make
right?
it to, so I had to stay at school to take this class.
Right. Uh, and then Grace, I guess.
Yeah, my name is Grace. I actually just graduated last year from GCU and I currently live in Phoenix, Arizona.
Okay.
I have heard your name so many times. I'm surprised that this is my first time actually seeing you, but I had Professor Phillips for pretty much all of my math.
Okay.
Um,
Okay.
but yeah, right now I'm teaching high school. I have Algebra 3, 4, and AP Pre-Calculus. And I'm teaching in Phoenix and taking this just master's program to hopefully eventually down the line do some maybe on the side teaching at a junior college or something like that. Just trying to keep my options open.
Okay. Okay. Good. Cool. And actually, there's two of you because Austin down here also was in
Mm-hmm.
a couple of my classes. So,
He and I run a
let
lot
me,
of classes
yeah.
together.
Okay. Actually, let me ask you one more question. I mean, is there some sort of direction by someone to get people coming out of GCU into this grad program? I mean, did someone mention that to you or?
No, I actually signed up for this program because I was really, really excited that it was offered in person.
Oh, okay.
And then about a week before I was supposed to start, my counselor said, "Hey, it's actually online. Let me know by the end of the week what you want to do."
I see.
And I
I
was like,
see.
"Well, I
Yeah.
guess I'm signed up, so I'll just go for it." But yeah, I
Okay.
signed up because I thought it was in person.
I see. Okay. Interesting. All right. I mean, if you want to meet sometime instead of meeting virtually, since you're here, you or people who are in
Yeah.
Phoenix, right? We could arrange that.
Hmm.
And then Richard, another Richard.
Yeah, it's funny because the last professor we had was also named Richard. So
Ah, that's right. Which isn't
yeah,
that common of a name.
yeah. So yeah, my name's Richard. I was I also live in Phoenix. I teach Algebra 2 and geometry as well. And yeah, I'm doing this program just to potentially teach, at a community college or like higher than that, even teach dual enrollment, and then even just learn like different things and that I can incorporate into teaching.
Yeah.
Like,
Okay.
yeah.
Cool. All right. Great. Kaylin, what about you?
I am from California, so I'm also with Lacey. We are an hour behind, so we're still in the 4 o'clock hour over here. Thankfully, today I'm home, but that's not always the case. So just kind of depends. I've got a little one at home, so hopefully she'll stay quiet with dad for most of the time, but sometimes that can be difficult being home with her in school. And then we're also expecting one in February, so that will be interesting.
Oh, wow.
Next.
Okay. Okay. So yeah, I think you wrote me about that, right? And I wasn't thinking about the time difference.
Yeah.
Yeah. Okay.
So.
Got it. Okay, Natalia, what about you?
Hi, I'm Natalia. I actually have been away from teaching math for about 4 years. I'm 6th grade science, but my previous years teaching, I taught 4th grade math and then 6th, 7th, and 8th grade math. I'm taking this program so that I can get out of the public school system and hopefully teach at I want to start off in the junior college or the community college level first, and then go from there. And
Okay.
I live in Surprise, Arizona.
Oh, okay. So you would also be like Maricopa.
Yeah, I'm just really west.
Oh, okay. Okay. Okay, cool. All right. And Austin, I know you, but introduce yourself too.
Hey, I'm Austin. I had Dr. K for undergraduate linear and discrete. I still live in Phoenix. I'm like 20 minutes east of campus. I'm taking this class because I'm interested in math, and it's, helpful as a public school teacher. You get paid a little bit more. And then eventually, if I want to do like college or anything like that, I'm on the right track. So, yeah.
And where are you teaching it?
I'm not teaching right now. I actually work for GCU.
Oh, okay.
I work for the College of Education, and then they give me a little discount on my graduate school. So.
Ah, I see. I see. Okay. Excellent. All right. Well, I'm Richard, your instructor. Let's see. I got my PhD at Berkeley, and I've taught lots of places, and the longest place I've taught anywhere fixed is GCU. So I've been here amazingly 11 years, which is surprising to me every time I think about it. And I guess we can get started. Okay, I already see time flies, right? So I will warn you, this is the first class probably where there's a lot of material, and it gets harder for this class and the next 2 classes, right? So the abstract algebra class and the real analysis class are a step up from this class, right? And this class is probably a step up from 220 or 525, right? Kind of depends on who you have, but my guess that's the case. I think your book is, first of all, your book is different. Okay, so how many of you have, I think there's like a raise hand. How many of you have some background in linear algebra, like have taken linear algebra? Okay, so Natalia, no. I guess everyone else said yes, and I guess we're still short some people. So, oh no, Drina said no too, right? Okay. All right. And let me see. Is there a David? Where's David Sabar? Oh, that's you there. Okay. Sorry, I'm seeing hands pop up in funny places here. So this text, you will notice, for those of you who have had linear algebra, is a bit different, right? And it sort of expects you to already be familiar with some stuff. So part of what we might do during some of these meetings, for some of you, is catch up on stuff that isn't familiar already. For example, Gaussian elimination and all those related things, right? And usually a good chunk of the course is about that kind of stuff, okay? We will get to matrices, but the book is a little different. I'll just say that, right? It's a little bit more algebraic centered as opposed to computational centered, right? Now we added the MATLAB stuff to keep some computational stuff in here, and there'll be a project with that, which is good, but unfortunately it adds extra stuff, you know, for you to do at the same time, right? And then of course these meetings are 2 hours long, and so there's no way to cover, like here we have 2 whole chapters of the book, right, to cover all that information in the meeting. So these are meant to be flipped classrooms, right? Now, for the other classes, I usually make my own videos, but this book came with a set of videos, which I think has the benefit of being pretty straightforward and easy to follow. I mean, I've listened to them all, and they don't get too deep into details, but they tell you enough, right? And I think in this class, the homework is actually pretty good. The text homework is pretty good. So if you're working on that homework and getting it, I think you will learn the stuff, right? I mean, you'll have to look back into the text and figure things out. But I think that's really how you're going to learn this stuff, is by doing the homework. Like, you know, reading the definitions, reading the theorems, that's all good, right? But you'll really get to understanding them when you start doing the homework, right? Okay, so that's my only sort of warning about the class. Let's see, there are a couple of things, and I do kind of leave this to you guys to some extent. Let me just paste something real quick. So I've got some sort of little bit of stuff that, I mean, I've sort of have some things to look through for the text, right? That I'm thinking about going through. But I also have some information on Gaussian elimination, because that's not directly covered in your text, right? And it is something that's sort of showing up on the MATLAB, but not too much actually. And then there's the MATLAB. So I think one thing to do might just be to make sure everybody's okay with the MATLAB. So maybe just work through the MATLAB with everyone. So you can see sort of what I expect. Now, some people have already turned it in. And one of you turned in a much more sophisticated version than I expected. And that does bring me to one other thing. And we haven't decided, first of all, this is the first time we've had a class that's been split into 2, right? You were in a class with 27 students, and then we split this class. So there's 2 classes running in parallel. And among other things, we would like to sort of make sure that the exams anyway, because a lot of points are in the exams, right, are kind of coordinated, right? So that means I need to get with the other guy and sort of figure out the sort of questions you want to ask, and also how it's going to be delivered, right? So that's the thing I won't be able to tell you right now, is how those exams are actually going to be done. Usually in my classes, they're take-home exams, and you have a week. But that said, that means they're a little bit more difficult, right? So that's the trade-off, right? If we do it in class, they've got to be a lot simpler. But then, of course, there's time pressure and, you know, all this other stuff, right? So there's sort of a trade-off between those 2 things. We are in an age of AI, right? And I use it all the time. And I use it to do math. I use it to learn math. And I'm always learning math too. And by the way, I don't find math easy. I find it really interesting. And I love learning it. And I go down rabbit holes all the time. But it does take work, and it takes work for me, and it'll take work for you, right? And it's perfectly fine if you want to use AI as a tutor, as help, and stuff like that. It knows a lot of stuff, right? And so it does make mistakes. So one thing you need to do as mathematicians is kind of, when it says something, you should make sure that makes sense. I mean, if you're using it for a tutor, right? Unlike some tutors, which maybe really know what they're doing, it really knows what it's doing, but it does do wrong things sometimes, right? So you really do want to sort of check and make sure that it's, you know, you're trying to learn from it, but you need to know when you're learning or when it's telling you something that's not quite right, right? And even more important is when we take tests, okay, so like I said, we haven't quite decided how we're going to do the test, but if they are take home, don't just use the AI to answer test questions, right? Don't just copy AI stuff into your answers. First of all, those you teach, so you probably see this yourself. It's easy to recognize right now when things are copied directly because of the way the formatting is and the way the language is and stuff like that, right? So that's one thing to avoid. But the other thing is it tends to go off and use stuff that you don't know yet, right? And when I see you using some theorem that we haven't even come close to talking about, it makes me wonder, right? And I will ask you to verify that you actually know what you're doing, right? So if you just pull off some weird theorem and say, oh, this thing you asked is really easy, just apply this theorem from 20 chapters ahead, right? Then I'm not going to just take that, right? I mean, basically, when you're doing your work, you should be using what you've been learning up to now, right? And you should understand every step of what you're doing, right? I mean, hopefully you like math, right? And so math isn't the sort of thing where someone tells you, oh, this is true, go use it. That's what we do in our 144 classes to students, right? For those classes where people don't actually need to know math, right? But here you're supposed to actually know what you're doing, right? And so you should know everything you're doing all the way along. You know, and maybe this is going to be the first class where you get to doing proofs, right? And that's the reason. So one little, I guess we're going to spend some time on some administrative stuff. I asked everyone to do 2 problems for participation, right? So the way I suggested us do this meeting will count 10 points. Okay, so the participation is 20 points. The other 10 points is supposed to come from those 2 questions you asked in DQ1. Whoop, hold on. Sometimes people come in, there's some feedback. Did that person stay or disappear? Not sure where they went. What was I saying? Yeah, okay, so a lot of people didn't do that, right? So several of you didn't do any posts there, right? And a lot of you did just 1, right? And so this time I'll let you go and do those retroactively, okay? But in the future, I want the first post to be done by Friday because I want to be able to look at them and give you some feedback, right? And I want the second post to be done by Sunday night, right? So that I can spend some time giving you feedback on what you've posted. And there's a very good chance that's going to be the only feedback you get on your work from me, except on the exams. Okay, so the homework, there's just if this class had 4 students, I would grade problems from every homework. With this many students, that's probably not going to happen. I'm going to look to see completion, right? I might look to see a couple of problems, like if I feel like people are trying to not do what they should do, that usually is not a problem. Then I might take a look at a couple of problems and grade those, more seriously. But the way I'm grading problems and for you to get feedback is to post things in that DQ form. If you have me for 513, that's what I do there, right? I have the students post problems in the DQ form. There are no MATLAB projects. There's no predetermined things, right? So that's just what they do for the DQs, right? They post problems. Sometimes 2 problems for each DQ or something, right? And who knows? We may do that this time too, on occasions. Let's see. One other thing is that I did design these classes. So there's only 6 topics. Weeks 4 and 8 are basically exam weeks, right? Now there are some projects and some other things that happen during some of those weeks, but there's no new material during those weeks, right? So among other things, they're kind of a week to catch up, right? So they're exam weeks, but also kind of catch up weeks, okay? And I guess the last thing to think about, and I have to warn my students always about this, there's a lot of free points in these classes. And that's a general thing about GCU classes, right? There's free, as long as you come and you do your participation, you're getting a lot of points there, right? And basically if you're doing your DQs, you're getting some points there. Those aren't so many points, but they still add up over some time, right? Projects, usually the projects are kind of teaching based, and usually you guys do pretty good on the projects, and I'm pretty lenient on the projects. Exams are what determines your grade, right? So you get a lot of free points, and you use probably like 500 free points in this class if you just sort of do everything, right? But the exams are also almost 500 points, right? So that's where I will grade things very carefully, and don't be shocked, right? If your grade changes a lot when you've had all these free points and all of a sudden you take an exam and get 60% on it, right? It's going to affect your grade. The other thing is, don't necessarily expect to get an A or an A+, right? You don't want a C. You definitely don't want too many C's in these classes because you can't have too many or else there's some problems, right? But a lot of people get B's, B minuses, that's good, right? It's still good. So I'm just warning you, there will be some aspects that might be new to you depending on where you've been coming from. I have a daughter in high school, and I know how grading is done there and how easy it is to get A's, right? And so don't expect that here, at least on the exam part, right? On a lot of the other stuff, that'll be the case, but not on the exams. Anyway, just a warning about that. Okay. Let me do one more thing. Let me take one more picture. Some more people came, and so let me just get one more snapshot here. We're still down someone, a couple of people, I think. Let me just stick this, actually, okay. Hold, sorry, just one second. Let me just do this. Okay. Okay, so maybe what I'm going to start with is I'm going to start with the MATLAB, right? And so we can just look at that kind of quickly, okay? And hopefully you've tried opening MATLAB and using it. I think you should have done that already in 509. So I think it shouldn't be completely new to you. And these are all templated. We don't ask you to do a whole lot of coding yourself. You can, right, if you want to. And like I said, one of you turned in a nicely coded sheet. So some of you probably know more MATLAB than I do. That would not surprise me. Let me share my screen. This screen. I think you can see that screen now. Right. Okay, so this is your MATLAB. I think you do need to have a couple of packages installed. So various points, I'm sure I've used the symbolic package, so you don't get like these long decimal place numbers, but you get pretty looking square root of 2s and stuff like that, right, when you're doing calculations. And I think eventually you need the stat package installed. Okay, that won't be till a bit later, but I think that's another thing you need installed. And all of this is through GCU, right? As a student, you have access to all of this. So nothing should be costing you any money, just to be clear. Good, all right. So who, raise your hands if you raise your hand if you haven't started the MATLAB yet. Okay, so a couple of you haven't started it yet. So I mean, part of it's really simple, name, date, one thing is I want you to turn in the MLX file. I want you to turn in the MATLAB file. The way I will grade it is I'll open it and run it and see what's there, right? If there's things you need to write those things in text, but basically I'll look at your code to make sure it runs, right? I never check numbers, right? I just check your formulas and see that they're doing the right thing. Right? It's kind of like checking your work or something, but checking numbers is a pain, right? I'd have to re-enter stuff and do all sorts of crazy stuff. Anyway, you enter your ID here, right? There shouldn't be any sort of brackets, or you just enter your ID. The way you run the cell is you just hit this little bar that turns blue over here and it runs. Actually, you might want to even start. Yeah, you might want to start by running this cell. Oh, that's what I did. It cleared everything, right? So it clears everything. No, it should clear everything. Let's try that again. Didn't I just run that? What is it doing? Well, let's not worry about it. It's I forget. Now I need to clear that thing. I need to add another line there to clear all that stuff. And let me not worry about this one. I want to just go down to the next one. So here in this part 2, right? So this is where we're looking at row reduced echelon form, and we're looking at this extra sheet for you to read about Gaussian elimination, essentially, right? So the first actual instruction here, I think this is probably not, or no, I think that is there. It's just maybe it's it's just text anyway. So maybe you just copy. I forget exactly. I've already filled this out. But I think maybe you just cut and paste this there, right? And so it generates a matrix. Putting the little semicolon keeps it from just showing everything on the side, right? And then this is the first place I'm going to use the sim, right? So this is making it symbolic. That makes everything kind of look pretty instead of having lots of decimal places over here, right? And then just putting the matrix back there again without that little semicolon will have it print the matrix, right? So, if I run that, I get that matrix there, all right? Now this sheet here talks about what row reduced echelon form is, okay? One thing about row reduced echelon form is given a matrix, the row reduced echelon form for the matrix is unique. Okay, so there's a function that can just give you the row reduced echelon form, right? So if I asked you all to do a row reduced echelon form of a matrix, you should all give me exactly the same thing, right? If I ask you all to give me an echelon form of a matrix, you may all give me completely different things. Okay, so that's not unique. So depending on how much we get to talk about the Gaussian elimination, we can talk about that. But here you would just run this, right? Or you might have, I think you have to enter this code, right? But it tells you what to enter right there. So it's not, I mean, this one's really just gives everything away, right? So there's the row reduced echelon form. And when you look at this, the leading one, in fact, the leading non-zeros. So row reduced echelon form has the leading things in each row to be a 1, right? Echelon form can have the leading thing in each row to be a non-zero. That's the only thing. That's the only restriction there. So you should go across, you have this kind of stair-step pattern as you go down, right? Where you go across and you hit the leading one. The next leading one should be further to the right, right? That's the way it goes, right? If you were doing this by hand, you choose this 9 up here and you use it to sort of kill off all the things below there, right? And then if you want, you can make that into a 1. I usually don't do that, right? But then you go to the next row. And if you can, you use the next thing to kill off everything below there. Use this row, right? So the order is really important here. Use this row to take care of this column, right? Then you try to use this row to take care of that column. And you just work yourself sort of diagonally across this thing, right? For some of the algorithms, you need to do it exactly that way, right? So you have to be a little bit, in other words, you don't want to pick the prettiest row or the prettiest column or something like that. You really want to be very methodical and work, top to bottom, left to right, right, in order for some things to work out. Anyway, we get our row reduced echelon form, so that's what it should look like. So this is an echelon form. Echelon form needs the same sort of stair-step thing. Row reduced echelon form, where we have this leading one, everything else is a 0. That's kind of the main thing, right? So everything else in that column is a 0. Okay, and then so these are called the pivot elements, okay, and the pivot columns are the corresponding columns, right? So that's a pivot column. So the first one is a pivot column, the second one's a pivot column, the third one and the fourth one and the fifth one are pivot columns, right? So there are 4 pivot columns here. And they're 1, 3, 5, and 7. So in this one, right, what I'm suggesting is you just write piv. So we're defining this, kind of array of numbers, just having those pivot columns in it, right? So that's what it is. Okay. And then what we're doing is we're taking from A. So we're coming back to this matrix. Now the reason this works, we might get around to, I'm going to include some notes where I have some notes on why this all works. But the ODE thing, right, this ode to, this note up here also explains it, right? So that, that's sort of extra reading. But you're going to take every one of these pivot columns, you're going to choose the corresponding column of the original matrix, right? So we're going to choose that column, this column, the 5th column, this one, and that one. We're going to choose those columns. So now this is some MATLAB. How do I choose those columns, right? So the way this notation works is I have my matrix A. That was the matrix we defined. I'm taking all the elements in the rows. That's what that colon means. Take everything from that row and take just those columns, right? 1, 3, 5, and 7. So that's what this kind of, what do you call this in computer science, where you have an array and you choose some part of an array out of it? Does anyone know? It's a very common thing to have to do, and every language has its own way of doing it. So sometimes it's called subsetting the array, right? You're having to choose a part of the array. So we're just choosing those 4 columns of our matrix A, right? The rank of A is the number of pivot columns. It's also the same as the number of pivot, well, the number of pivot elements, right? So that's what that is. Okay. There's no real notion of pivot rows. There's some non-zero rows here, right? If you look at A, if you look at the reduced row echelon form, there's these non-zero rows, right? But you could call them pivot rows, but it doesn't really apply back to A. There's a sense in which these rows, they're related to this matrix, but not directly related to this matrix. In the same way, these columns are directly related to this matrix. Okay. So what we want to do is we want to reconstruct A as something built out of those pivot columns together with the reduced row echelon form. So you take the pivot columns, you take the non-zero rows of the reduced row echelon form, okay? This is called C, this is called R, okay? And you multiply those two things together and you should get back A, right? So that's, and this, all you're doing here is sort of verifying that. You're not really being asked here to understand or explain why that's the case, right? Here you're just sort of given that, it's one of those places where you're given this as a fact and asked to verify it. The note that you're supposed to read does talk about why it's true, right? And then I'm going to give you some other links to stuff where I talk about why it's true. And depending on how much time we have, we may talk about why it's true today, right? Depends on what we end up doing for the majority of the day. But part of the point here is everything I did here is sort of described up here, right? So kind of if you follow the instructions, you should be able to do this. For those of you who haven't started, should be able to follow what's up here to enter the code. And this should be the case for all of the DQs, right? So they're all sort of like this. We don't ask you to do too much independent coding with MATLAB. And then, you know, this don't mess with that just means that. If you mess with that, it changes everything up there. Good, okay. And by the way, you need to keep it in this MLX file. Don't change it. Some of you may have used MATLAB a long time ago and there were just .m files. Don't change it to .m file. Leave it in the .mlx file. Okay, so that's important. Yeah, any questions about that? I mean, yeah. Oh, someone keeps coming in and out, maybe.
And you want us to just type our answers to the part 1 and part 2 discussion in the file, like right underneath where part 1 discussion? Okay.
Yep, and in fact, you know, you can play with it some. Like if I want to type, it's been a while since I've done this. Yeah, if you want to type if you want to put in a matrix, right? I think you can click here. Let's see, insert a, where's a matrix? Oh yeah, matrix, right? You can put matrices in, right? You can put math in. If you know LaTeX, usually I just go for LaTeX. You can use LaTeX, right? So you can put math into these things. I mean, I guess this one doesn't have a whole lot of math in it, but sometimes you'll see where I write this stuff and it's got a bunch of math in it too. But you can, yeah, so there's, you know, play with it, get used to using the editor there. You can make things bold, you know, that sort of stuff. Put in links, whatever, right? So I mean, it doesn't hurt to learn how to format stuff using math. I mean, you're all teachers, so that's a useful thing to know how to do, right? And so it's a useful little editor. It's not the best thing in the world, but it's okay. Good. Any questions about that?
I have a quick question.
Yep.
On my computer, when I hit run, it says that there's an unrecognized function or variable random sample or rand sample.
I wonder if that already uses stat. That might already use the stat package.
Okay, so how would I, under apps, I'm assuming, and what's it called?
I think it's called maybe it's called statistics. Yeah, maybe
is
install.
It optimization? Is it optimization or it's called statistics?
Let me see. It's been a while since I've this is something I've done in a long time. So let's see. It's not that. Let's see. Get more. I don't think this is called an app, but let me see. So when I click that install more apps, it pops up this thing. Oh, maybe this is it. Let me see statistics. What is it called? wonder if I can see. Let me see what I actually have installed. Let me see if I can see that.
Okay.
No, that's not what I want. I think. I don't know. Does anyone know how to check this?
Does the drop down on the right do it?
The one
Next to where, yeah. And then under, mine has one that says My Apps under that. Maybe not then.
just trying to remember. Well, I guess one thing to do would just be a search, right? Ah, maybe this is a good place to use some good old AI, right? That's good. It's good for coding, right? It's really good. Like if you run into something in MATLAB or something, it can basically write the code for you. And what is the function? So in MATLAB,
The message that it's giving me is unrecognized function or variable, and then in quotes, rand sample. And then it says error in the document title. And then gen mat, line 22.
V toolbox is almost means so. Oh, it's statistic and machine learning toolbox. So we saw that in that list, right? So that must be the one you should install.
Good.
So maybe they've renamed it to add that.
Okay, do you know how I get there to install something? I'm not sure.
Okay, let's see. So so I think here, right? So install app. No. Sorry, let's try that again. Get more apps. And so that brought me to this page. You might just try it at the same time. So machine learning.
Yeah, do it. Machine
learning. It was
learning.
right there. I saw it. Oh, there. No. God, it was right there.
I got mine to pop up, so I'll go ahead and click.
Oh, maybe because mine is already installed. Maybe it's not adding that, offering me that, right? So it was machine learning and statistics toolbox, right? And so maybe you download it, and then maybe it doesn't install automatically. You have to download it. Maybe that's what I'm guessing. And then once you have it downloaded somewhere, you click this install app, and you choose where you downloaded it to, and click on it. That's what I'm guessing.
Okay.
Right. So yeah, give that a shot and see if that works.
Okay. Thank you.
Okay. Good. All right. Problem solving is good. Good. Any other questions on that?
I do have a question.
Yep. Go ahead.
Sorry, I do have a concern. So I'm having trouble uploading the MLX file on MATLAB.
And why? What is it?
I'm
I mean,
not
what sort of error
sure.
is it giving you?
So when I downloaded it, I don't know why. I'm not sure. Because I would go to open on MATLAB and it doesn't show up for some reason.
Are you using the school's MATLAB or using some old MATLAB that you had previously?
This is the MATLAB that I downloaded here. This is through the school. I mean, let me double check. I mean,
do you have two? I mean, there didn't used to be MLX files, so it almost sounds like you have an old version of MATLAB. But if you have the one that's downloaded through us, it should be relative. I mean, it's been a long time that they've had them, so it'd have to be a pretty old MATLAB to not recognize MLX files. And is there a chance that the name of the file got messed up or something?
I'm not sure because when I downloaded it, it's Mat512 RST1 DQ2, right?
That sounds right. So here's
Um,
another option too. You might just try this. I mean, if you run into problems, you can
Yes,
log into your account and open this in MATLAB
yeah,
Online.
I could try to just go to MATLAB and
Because then everyone should see exactly the same thing here. And probably those
Place
packages
everything.
already installed and everything's.
MATLAB. Yeah, so open MATLAB Online.
Yeah, it's a little bit slower, right? But it should work. I don't think you need to worry about installing most of these apps. I think they should already be installed. So that's an easy option, right? Just use that.
So in order to upload it, you would just go to open and it should show up, right?
I think.
Because the problem is that it just doesn't show up and I downloaded it.
So okay, so the interface is like this.
Let me see. Unless it's maybe some it might have gotten lost in my computer.
This is a good question. Let's not spend too long on this, but
okay, it's
if
fine.
you can hang out
That's all
afterwards,
good.
let's play with it a
Yeah,
little
of
bit.
course. Sorry, it's all good.
Because I think maybe you need to upload them. If you're using it online, you might need to upload it to the online drive. That's what I'm thinking you might need to do.
Yeah.
On my computer, I have it so that the online drive is actually connected to my drive virtually. So everything's in the cloud.
Easier.
Yeah.
Okay.
So that's a thing you could think about doing too.
We could discuss it later. It's no worries.
Yeah. Okay.
Yeah, thank you.
This. Okay, good. All right. So real quickly, let's just look at some linear algebra. Let's get started here. So first of all, the book. I'm just going to go through what the book does. I'm going to go through it pretty fast and slow down where you want me to slow down. Okay. So it starts off with the real numbers, which you think you understand now, and you will think you understand that till you get to 571, where someone will convince you that you don't yet. But I think you know what the real numbers are. And then you have the complex numbers. Okay. There is a lot to say about the complex numbers. Okay. So let me just, when you look at what I do, and by the way, so there's two things I'll apologize for ahead of time. My handwriting is really bad. And also my voice goes out while I talk. So sorry about that. Can't do anything about either one of those two things. Okay, so e to the I theta is cos theta plus I sine theta. And this is the sort of thing that you do with infinite series. There's many proofs of this thing, right? You could just take it as a definition. I mean, there's lots of options here for why that's true. But it turns out to be really useful, right? Because the polar form of a complex number, right? What you do to get the polar form is you take this and divide by its length. What's the magnitude? So this is z, right? The magnitude of z is, in fact, the way we're going to do is magnitude of z squared. The complex numbers are really important because they reflect a bunch of stuff that happens in linear algebra. We'll see this as we go. But one way is writing it as zz bar, right? And so this is a plus bi times a minus bi, right? Like that. And this is, of course, just a squared plus b squared. So this is the length squared, right? So the length, of course, is just the square root of that, right? The square root of a squared plus b squared. And so what you can take any complex number and write it in polar form, right? As its length, right? Plus this part over here, plus this sort of, sort of z divided by its length, right? But this has exactly the form, right? So this is going to be a over a squared plus b squared plus b over a squared plus b squared I, right? And this thing and this thing are going to satisfy this squared plus that squared is equal to 1, right? So they're sitting on the unit circle, right? So they are sitting at an angle theta, right? Okay, so this is really the same as the length of z and then some e to the I theta, where theta is kind of what's called the argument of z. So that would be the angle at which it's at, okay? And you can view this too if you think of C as just sitting here in the plane, right? You can think of elements of z, a plus bi, as vectors, right? In the sort of sense that all of you understand vectors, right? And of course, there's an angle theta, so that's the angle theta there, right? Okay. So anyway, when we do stuff with complex numbers, you will see that a lot, right? You'll see me using this because it's very, very convenient. Okay. And you've seen that in some of the DQ responses already, and someone asked me about it. So this is just a thing to keep in mind. And of course, the point is when you multiply complex numbers, it's clear why you sort of get rotation here, right? Because if I multiply, e to the I theta 1 and e to the I theta 2, well, now you're just dealing with algebra, right? So this is e to the I, theta 1 plus theta 2, right? So you just add the angles, right? And of course, the links just multiply, right? So it's kind of like two different actions. Part of it is a stretching, right? And that's multiplicative, and part of it is this addition, and it's additive, right? Part of it is this exponent thing, and it's additive, okay? That's probably the main thing I want to say about complex numbers. I mean, keep in mind what the z bar is, keep in mind this thing. We will later on get the polar form of matrices. It's going to look a lot like this. It'll look like sort of a scaling matrix together with let's call it like a scaling matrix together with a rotation matrix, right? So we'll have the polar form of matrices. So a lot of things are reflected in matrices. Also, the inner product is sort of heavily reflected in this thing here too, right? So it's useful to sort of understand and get used to complex numbers. In your book, the only fields really used are the reals and complex numbers, right? So when it says F, it usually means the reals are complex numbers, but you should keep in mind that for most things in the book, it doesn't matter, right? So you can have other fields too. And when you get to 513, you're going to need that, right? So you want to sort of keep that in your head. A nice other field is Q, right? You can multiply, add, and divide in Q, so it's a field, right? And well, I don't want to jump ahead, so let me just stop there. Okay, so anyway, any questions about CN or RN? I mean, you do have you have notions of length in both of those things, right? Euclidean length, etc. Right? Is that all good? Are you all good with that?
I do have a question.
Mm-hmm.
Is that A equals SR?
Yeah, I mean, this doesn't mean anything right now, but it's like a scaling.
Oh, it's scalar and then
In a
R
rotation.
Rotation. Oh, scaling rotate. Okay.
I mean, this is something we'll learn right at the end of class. So it's a long time in the future, right? I'm just saying that. Yeah.
It's relevant to the rotation matrix though, right?
It will be, yeah. So yeah, we'll have lots of factorizations of matrices.
Okay.
And this polar form will be one of them. I mean, we just saw one. We just saw how to take A and use Gaussian elimination to factor it into CR, right? So that's an important one, right? And in the notes that I'm going to give you, there's also an LU factorization that's really important, right? So many of the things we look at in this class will be this factorization of, and the way we'll often say is factorization of matrices, right? The way your book's going to explain is factorization of linear operators, right? So we'll have this sort of back and forth between linear operators and matrices. So that's going to be another sort of thing we look at, but different ways to factor stuff is going to turn out to be really important. Okay.
Right. Thank you.
Yeah. Everybody, if I gave you like 2 plus I 3 minus I 4 as a vector, right, and said find the length of this vector, you could all do that, right? I'm seeing some heads shaking. No, I'm seeing you do have you can turn on your microphones and talk too, right? Right. So I mean, this is all the Euclidean length, right? So these Rn, Cn, right? The length in this is all like Euclid, right? So the length squared is going to be the sum of the squares, right? So if V is, Z1 through Zn, it doesn't matter if it's real or complex or whatever, right? Then the sum of the squares of these will be the lengths of those squared, right? Okay, and so the final length would be the square root of that, right? So the square root of the sum of the squares. Right. So it's the usual norm, and it works in reals, it works in complex, etc. Right. And for those of you who teach statistics, right, this should look really familiar, right? And this sort of stuff comes up all the time. And so we'll see things, statistics is a lot of linear algebra when you're doing multivariable stuff, even when you're doing single variable stuff, right? It's a lot of linear algebra in there. So we'll see that sort of stuff pop in as we go. Okay, this book jumps right into vector spaces. So you're just given some axioms, right? Anything that satisfies those axioms is a vector space, right? The one thing that's sort of fixed is a field, right? You're working over a field. And so your book just calls this F, and so usually it'll be C or R, right? I'm saying you also have Q, right? That's an option for a field. If I get to it today, I would like to say some things that work, like why is it important that this is a field and not something that's not a field? Right, so the integers, by the way, these notations, right? Complex reals, rationals, integers, Z, right, is integers. N, right, starts with 0 in my world and goes on. Doesn't start with 1. Okay. Right, but this is an algebraic structure too, right? There's addition and multiplication, right? All that sort of stuff, but there's not division, right? So it's sort of useful to look and see where is it important in what we're doing that we're actually using a field here, namely where are we using division, right, in some of the stuff we're doing. Okay. Some kind of strange vectors. Well, first of all, C is a vector space over R, right? So just in terms of, I mean, I'm ignoring simple examples like Rn is clearly a vector space, right? Cn is clearly a vector space. So those are the obvious ones. It's kind of the bread and butter vector spaces, right? And in Rn is the one where you can draw them as, arrows, right? So like R2, you draw those as arrows in the plane and stuff like that, right? So that's here. Cn, you can't do that. You can't just think about an arrow in the plane in Cn, right? Because just the two-dimensional, just C squared is actually a four-dimensional space, right? In some sense. So you can't visualize things in the same way there. But C is a vector space over R, right? And it's how many coordinates do I need to describe an element of Z? So Z is A plus BI, right? Where A and B is in R. And this is just what we teach kids, right? So, we sort of treat that as this vector, A, B, right? So it's kind of and we haven't got to this thing on dimension yet, but this number is associated to that vector, right? So the complex is a two-dimensional vector space over the reals, right? So the reals is a vector space over Q, right? I can take my field to be the rationals, right? I can take my vectors to be reals, right? And I can verify all of the properties for R being a vector space over Q, right? So this would be not only an infinite dimensional vector space, but a really, really large infinite dimensional vector space over the rationals, okay? So there's some sort of strange examples. An interesting example is this one. This will come up a lot in the next class you do, but like Q square root of N over Q, where N is not a perfect square, where a square root of N is not an integer. Right, and what would this thing mean? So it means this. It means all the things of this form, A plus B square root of N, where A and B is in Q. All right, and how do you do division. And by the way, I'm not assuming that n is positive, right? So if n is -1, then this would be qi, right? If n is -5, it would be q square root of -5, right? If n is 5, then it would be q square root of 5, right? Okay. How do you compute something? So I'm saying this is a field, right? So y is 1 plus a b square root of n. What would 1 over that be? How do you calculate that? What do I multiply by to calculate this thing?
By the conjugate?
That's right. So we still have this notion of conjugate, and it's going to be like this, right? Right, and so this will, so what'll happen down, so what does this bottom part become? It becomes a squared, minus b squared n, right? So what the bottom becomes, right? So this will be a, and then a squared minus b squared n, plus b, right? A squared minus b squared n, square root of n, right? And these are still rationals. What is the one thing you have to be careful about here? Dividing by a minus b squared n, right? I need to know that a squared minus b squared n is not 0, right? So that's important. So if this were the case, n would be equal to a squared over b squared, right? That's a rational, right? Because a and b are rationals, right? Okay, but then the square root of n would be a over b, so it'd be rational. Okay, so here's a little bit of, do you remember a little bit of things about numbers? If the square root of an integer is rational, what do you actually know about the square root of the integer? This would be a good thing for you to try to prove. This is like a proof by contradiction is the way you do this, but I'm not going to do the proof right now. I'm just seeing who can give me an answer. So if I take the square root of an integer and it turns out to be rational, what can I actually say about the square root of this integer?
It's a perfect square.
It's a perfect square, but in particular, it's an integer, right? So all I know now is that this is rational. So if the square root of n is rational, then the square root of n is actually an integer, right? So that's an important thing to keep in mind. Okay, so that doesn't happen, and so so this method of taking an inverse works, and so we have a so these things are actually fields, right, over Q. Okay, so this gives us a supply of other fields to play with if we want to, but this is also just like with C over the reals, right? This is essentially the same construction, right? We're taking something, we're adding square root of n. To get C, we take the reals and we add square root of -1, right? It's essentially the same construction. This is a two-dimensional vector space over Q, right? Okay, so we've got these things that can play both roles. It can play the role of a field, and it can play the role of a vector space, right? So both at once, okay? And this is going to turn out to be a really important one for 513. And I just finished teaching 513, so it's sort of in my head right now, okay? What are some other important ones? So maybe everyone give me some important vector spaces. Because your book also tells you, but especially those of you who had linear algebra, but your book does have some. So so we have these two basic ones. Let's leave these out. What are some other important ones? What's one your book talks about? Two your book talks about.
How about the one for polynomials?
Exactly right. So the polynomials over F, over field F.
Yeah.
Sometimes this is abbreviated f of x because you're taking coefficients from F and adding variables, right? So this is a notation you might see me use. But yeah, so these are the set of all summation ai x to the I equals 0 to n, right? For n some natural number, right? And these AIs are in the real, or in F, right? Okay, so there's no restriction on the degree. These can be arbitrary degree polynomials, right? And then another one is related to this as what?
Can you reread that last line? I'm writing it in my notes and I can't.
Oh yes, and also I'll make this available to you too. But this is the summation from 0 to n, a sub I, x raised to the I, right? And then n is just coming from the natural numbers somewhere, and the AIs are coming from the field F, right? So their coefficients are coming from F, right? So an example of something in here would be like 3 plus 4x minus 5x cubed plus x to the 4, right? That would be a polynomial in there, right?
And then that says N and A and F.
AI.
AI.
So the coefficients, right? Those coefficients. So what's a polynomial? What's a vector space related to this? Your book gives 2, and they're both important for this class. Polynomials turn out to be really important in this class, so they're worth going into a little bit. And some of you did this for your homework. So P M at F, right? So these are just the polynomials of degree. So what are they? Are they polynomials of degree exactly m? Are they polynomials of degree less than m? Are they polynomials of degree up to m? It's actually a good.
I think it's up to m.
So up to m. Okay, so these are things like this, right? Summation ai x to the I equals. So it's starting at 0, going all the way up to m, right?
Okay.
Then all the rest is the same. AI is an f, and that's it. There, m is fixed now, so we don't have that other bit, right? So just that. Okay. And I asked someone in class this, so this is a vector space. Like, what is the addition here? We take 2 of these things, right? And this is very, very common. Bi x to the I, right? And what you do is you just pull the xi's out and combine the coefficients. All right, so that's how you do vector addition, right? Scalar multiplication, you just, you multiply one of these things. I'll just write it down. All right, alpha summation I equals 0 to m ai x to the I, all right, is going to be summation I equals 0 to m alpha ai, right, x to the I, right, like that. So the usual things, right, sort of what you would expect. Okay. Why would this not be a vector space if I said let's restrict to polynomials of exactly degree m? Why would that? What would cause a problem there? And one of you did this already on your DQ. You can answer if you want.
I was the one I think you asked, and when I was analyzing this and I was getting stuck of what was up to, my conclusion was exactly means that a to the power, or your coefficient a of n for your highest leading degree cannot be 0.
That's right.
So it won't be a vector space because you don't have that 0 element.
Good. Okay, you don't have the 0. That's an easy one, yeah. And it's not closed under subtraction either, right? Which is what came to my head first, but that's a better answer. Yeah. So when you're trying to show something's not a vector space, starting by showing 0's not in it is a really great way to start, right? Because that's sometimes the very simplest thing. Good. All right. Good. Okay. Your book does have a couple of first of all, you need to know all those axioms, right? You can keep a list. I mean, you can use it, whatever, but you do need to know how to check all those axioms. And that is what I need you to do in the first DQ, right? If you haven't done that, I need you to check all those axioms for the thing. And then there are a couple of theorems about that aren't given in the axioms, right? And they're very simple, but they're really useful. So one is this, right? The uniqueness of the inverses in identity, right? So if I have so I'm in a vector space over F, right? That's sort of where we're living here. And I have something that looks like, it sort of behaves like the additive inverse of A, right? Okay. This uniqueness proof says, well, then I know that B is minus A, right? There's only one thing that behaves like the additive inverse of A, right? So we actually use this sort of uniqueness, and I think I might show you one of these other proofs, right? So this uniqueness proof is really simple. So I'll just let you, if you haven't thought about it, think about it. The other one is for the identity itself, right? If I have A plus B equals A for all A, in fact, if I just have A plus B equals A, I don't even need for all A. If I just have A plus B equals A, right? Then I know that B is 0, right? So we have a unique thing. Like if we have something that behaves, this is like walks like a duck and quacks like a duck, then it's a duck kind of thing, right? So if it behaves like the identity, it is the identity. If it behaves like an inverse, it is an inverse, right? So let's actually look real quick. And again, this is one that came right out of one of the DQs you guys did. If we look at this example, so there were two, like, I think these are both in DQs, so that 0v is equal to 0. And one thing here is sometimes it's worth, like, this is the 0 of the field, right? These are both vectors, right? So in my notes, I tend to make the vectors bold just to make them look different from the field elements. But if I don't, right? If I just wrote this, you have to sort of in your own head think, well, that's a vector, that's a vector, that's a scalar, right? So you want to keep that in mind, right? Different types of objects there. So this is one that is, I think it was in your homework, right? And then this is another one. So this one actually doesn't use this uniqueness, but this one did. So it's sort of fun to look at. So you're showing that minus 1v is minus v, right? And the proof someone gave, I think, is you want to show, I mean, basically, given what I just said, I need to show that minus 1v behaves like minus v, right? So what I need to show is I need to show whatever this minus 1v thing is, right? I need to show that when I add it, see, I can't write minus v yet because I don't know it's minus v, right? When I add this funny minus 1v to v, right? I want to show that I get 0, right? And now we use some of our axioms. V is equal to 1 times v. That is actually an axiom, right? So that's actually an axiom. And then what can I do with this is I can use distributivity, right? So this is 1 plus minus 1 times v, right? So we're using those axioms, right? We're using this axiom, we're using distributivity, right? And now this is 0 times v. And we're assuming we've already proven this bit up here, right? So this is 0, the vector 0, if you like, right? Okay, so what have we shown? Well, we've shown that this funny thing here, when I add it to v, gives me 0. And then, you know, for a correct proof, you need to say by uniqueness of the inverses, right? That minus 1v thing is minus v, right? So you're actually using that stuff, okay? So not a lot of sort of results here, but there are these kind of 4 results, these 2 uniqueness results and these 2 results there. Really simple, but worth kind of thinking through once, okay? Any questions about that? Definition of vector space. If you haven't had linear algebra before, that's bound to be a new kind of thing for you, right? I'm guessing. So it's like, what is a vector space? It's not just sequences of numbers, right? It's anything that happens to satisfy those things, right? And vector spaces can get super abstract. And when you go to further math, they can be high dimensional surfaces that intersect in certain ways. They become all sorts of things, right? So it is an abstract, it's your first abstract algebraic structure if you haven't seen it before, right? So 513 is all about abstract algebraic structures. It's about groups, rings, fields, all those things, right? Vector spaces is your first pass at a sort of a completely abstract algebraic structure. Anything that satisfies those axioms, that's what a vector space is, right? Anything that's in one of those vector spaces, that's what a vector is, right? It's not an arrow, it's not a sequence of numbers, it's something in a vector space, right? So that's the sort of level of abstraction that's here, okay? So polynomials can be vectors, functions from a set into the field can be vectors. Another good example is matrices. Matrices are vectors, right? So lots and lots of things. Many things turn out to be vectors. Continuous functions are vectors, right? If I add two continuous functions, they stay continuous, right? You prove all these things in calculus classes, right? So the next thing is we have a vector space. What is a subspace? Well, a subspace is just a subset, which is also a vector space, right? And then what do I need to show? So suppose I have something that's a vector space, and I have a U, which is a subset of that vector space. What do I need to show that U is a subspace? There's either two or one thing. It depends on what you want to, how you want to do it. Maybe three things.
Is it when U spans on V?
No, this is different. So we haven't got the spanning or independence or anything yet. I'm just saying, when is U a subspace of V? Not just a subset, but a subspace.
When it's closed under addition, scalar multiplication, and it has 0.
That's exactly right, right? So what you need to know is you need to know that for all U and V in U, right, U plus V is in U. Now, you don't need to check this for the actual vector space, right? Because whatever the vector space is, it's got an addition and multiplication, which is defined on that vector space, right? So closure is for free on the vector space, right? But when you're in a subset of the vector space, closure is not for free, right? So like if I took the plane, which is a vector space, R2, right? And I just take all the points that are up here, that's a subset of the plane, right? Is it a vector space? Like, what fails about being a vector space here? Like, if I take a couple of vectors like this, is it closed under addition? Yeah, right. I mean, and geometrically, right, you get this kind of parallelogram rule thing, right, for adding vectors like that. So all these points out here are closed under addition. If I'm including this, it also contains 0. Well, that's good. What's the problem? Is it closed under scalar multiplication? Yeah. Right? Like what is -1 times this vector? It's this vector over here, right? And that is not in the set, right? If I'm just looking at this upper, first quadrant stuff, right? Okay. Yeah, so you need closure under addition, closure under scalar multiplication, and importantly, you need to know that 0 is an element of U, right? Or equivalently, you need to know that U is not empty. You need to know one of those two things. Those are equivalent to each other, but you need to know one of those two things, right? Why are these equivalent, right? Because if I had something in U, right, and I have that it's closed under scalar multiplication and addition, right, then I have that U plus minus U must be in U, right? So that's saying that 0 is in U. Right, okay. Good, okay, so when you're showing something as a subspace, basically you show those three things hold, right? Okay, so whenever you're tasked with showing something as a subspace, you need to prove those three things. I promise you, you'll see that something like that somewhere in a quiz or in a test or something. This notation, when we're by context, right? When we're talking about spaces, and I write this notation, I will mean subspace, right? So it kind of depends on the words around it, right? But if it's specifically a subset, it should be clear, right? If I have two vector spaces, right? If we know U and V are vector spaces, right? And I write U subset of V, I mean use a subspace of that vector space, okay? So in other words, I'm saying that the addition and multiplication on U is the same as V, right? Okay, just notation there. More notation, we have two sets and I add them together, right? What I mean is the set of all U plus V, where U is in U and V is in V, right? So we can add sets together. I mean the set of all those things inside there added together, okay? So for example, if I said A plus V, right? Where this is a single element, I would mean the set of all A plus V, where V is in V, right? So hopefully the notation is kind of clear. Same thing if I put a multiplication here. If I put a multiplication, these are sets, right? I mean the set of all multiples of things that are in there, right? Good, okay. Suppose U and W are subspaces of V, right? Is it true that U, the set U plus W, is a subspace of V? So here I mean subspace. I need to ask that because we don't know it yet. Okay, so let's just check real quick. Is it true that 0 is in U plus V? So right now it's a question mark. We haven't proved it yet, right? Okay, these are both subspaces, right? So is 0 in U? Is 0 in V? So is 0 in U plus V? How do I know that? Because 0 equals you guys can turn on your microphones and talk when you want to. I see mouths moving. It is
Zeros in U and in V. Couldn't we just add those two zeros together to keep the zero in U plus W?
Yep, you need, but you need to show that 0 has this form, right? The things in here are of the form U plus V for something in U. And so you need to actually write this, right? So 0 is 0 plus 0, okay? And so now if I have U plus V in U plus V, and I have U prime plus V prime in U plus V, right? What do I need to show? I need to show that U plus V plus U prime plus V prime is in U plus V, right? Okay. And what sort of things am I going to use to do this? This is real algebra here, right? Like, can I get rid of parentheses and can I move things around and why? Right? I mean, can I do things like this? Like this is the same as U plus V. I don't want to do it too formally, so let me just get rid of all the parentheses, right? And then I can like flip these around. Right? So we're using associativity, we're using commutativity, we're using all those things, right? So when you have associativity and commutativity together, right, you don't really have to worry about order or parentheses when you're adding, right? Which is fantastic, right? It allows you to like dump a bunch of stuff into your grocery cart and then go pay for it by pulling one thing out at a time and not worrying about which order you do it in, right? So I mean, we could just look at the sum of the, you know, U1, U2, U3. This makes perfectly good sense where I have, you know, the sum of a bunch of things as in a set, right? With no particular order, right? Sets don't have orders, so in any order at all, right? Then this would just, you know, it doesn't matter what order I do it in. I mean, I can't write things down without writing it down in an order, but hopefully you get the idea, right? Okay, but you are using the axioms there, right? I mean, you're using those axioms. And then, of course, you need to show closure under scalar multiplication, right? So same thing, take this U plus V, right? I just wanted to work through one of these, right? Then alpha UV, U plus V, whoops, right? By definition is alpha, but sorry, not by definition, by distributivity, right? Alpha V, right? And so now this is in U, that's in V, right? So this is in U plus V, right? So that's the kind of thing you have to do, right? Makes sense? Hopefully, good, okay. Good, and you can add together more than one vector space. You can add together a bunch of vector spaces, right? So you have V1 plus V2 plus, you know, spaces, right? You could have V1, V2, Vn. We're going to do this later on a lot, right? Subset of V. Then we can look at the subspace. Okay, like that, right? There's this other notation. Let me just do 3 sets, right? Okay, so what this means, so if I say W equals this thing, right, it means that W is equal to the sum the way we just defined it. So we're just adding things together. Okay, but in addition, right, it has the property that there's kind of no overlap in what comes in here. So there's a complicated way I can say it. Let me do that once. So it means that V1 plus V2 intersect V3 is, now is this going to be empty? Is that a reasonable thing to say?
Is which part going to be empty?
So could it possibly be that V1 plus V2 intersect V3 is empty?
Would it
Yeah.
have 0 in it?
It's got to have 0, right? So the smallest anything can be here is singleton 0, right? But that's what it has to be, right? And then we also have to say V1 plus V3 intersect V2, right, is small, right? And then maybe we even have to say V2 plus V3 intersect V1 has to be just as small as it can be, right? So we're sort of saying there's independence in some sense between those various things there, right? An easier way to say this is to say if I take V1, V2, sorry, if I take, let me try that again. If I take V1 in V1, V2 in V2, and V3 in V3, and they're all non-zero, right? So I should have said minus 0, right? So V1, V2, V3, not 0. And then A1, V1 plus A2, V2 plus A3, V3 equals 0, right? If this happens, then A1 equals 0 equals A2 equals A3. So the only way to put them together and get 0 is for all the coefficients to be 0, right? So this is easier than saying all of these various ways of taking these intersections give you the smallest vector space, right? Okay, and what is a way of saying this? I mean, this is jumping ahead from this section, but what am I really saying about this V1, V2, and V3 by saying this?
They're independent, is that right?
They're independent, right? So once we have that word under our belt, right, I can say W equals V1 plus Vn. It means two things. It means one, W is just the sum of these things. So everything in W is a sum of things from these individual pieces, right? And two, if I take V1, sorry, Vi in Vi minus 0, so take it something to be not 0, right? Then the set V1 through through Vn is independent. Right. So it really means those two things. So it says everything in there is a sum of a particular sort, and you've got this kind of independence between the various vector spaces. Okay.
Is this kind of like how independence is defined in like probability?
Independence and probability is a very different thing, I think.
Okay.
Right. Yeah, I mean that's a very different concept. So the word independent gets used for a lot of things, right? So this is definitely a different concept from that. I mean, independent and probabilities, yeah, let's not go down that path yet, but I mean it is a different thing, right? This is a kind of algebraic independence. It's a very common algebraic independence, right? Here it's an independence over sort of addition, and we could have another kind over a multiplication, right? So there's lots of independence in algebra, and so this is that kind of thing. If it were multiplication, I would need to have the multiplicative identity there, not the additive identity, but there's that kind of thing is pretty common. Good, okay. And so these are ways of building subspaces, right? And part of what we'll do in this class is we will build subspaces of some fixed space, right? And often that's going to have something to do with these decompositions of matrices, right? So this kind of thing is going to go hand in hand. So taking algebraic structures and building new algebraic structures by adding them together or quotienting them or doing other stuff, right? That's going to be part of what we're doing, right, in here. Any questions about subspaces?
I do have a question on the second one, on number 2.
Mhm.
Where it says VI in VI minus 0.
Yeah.
Oh, okay. Just
So
making sure.
this is taking away the 0 element, right?
The 0 element, right?
Yeah.
And the
So
okay,
the,
I see. And the okay, got it.
the way I write set differences is like this. So this would be the set of all S and S, where S is not in T, right?
Oh no, yeah, I see.
So that's the notation there. Sometimes
I
you'll see
just-
this written like this, right?
No, I just didn't see the I don't know if it was a minus or a dot there. I'm just
And bad notice there is a problem with notation here because this does not mean the set of all things here minus 0, right? So it's kind of contradicting the previous notation I had. So again, there is context used, right? You do have to think about context. when
yeah,
you're
because
writing
I'm used to
things.
seeing it with the slash.
Yeah, so if I put a slash, I wouldn't have to worry about context, right? So if I put the slash
So-
there, that'd be maybe safer, right?
Okay, thank you.
That's it for chapter 1, right? So any questions about any of that? So I'm going to move on.
I don't know if we would have time, but 1C number 9, I was pretty stuck on that one. Would it be
Let me-
possible to look at that one real quick?
Take a look. Yep. So you can always do this. You can always take control and ask me to do stuff. Because we really don't have time to do everything. So let me go down and find this. Oh, sorry, 1C number 9. Sorry, you said 1C, right?
I don't know if this is helpful, but for that one, I picked 2 periodic functions.
Mm-hmm. So,
Um,
so this is an interesting one. It's actually, I think, not so easy. And I wrote this to one of you. Suppose I change this question a little bit, and I said, let's look at the set of all. And again, so these are functions from the reals, right? Yeah, reals to reals, right? Suppose I looked at the set of all f from R to R. Whoops. Where f of x plus p equals f of x, right? And this is going to be the set of all p periodic functions. Is that a subspace? So the p period, so p's fixed, right? Is that a subspace? Is it true that if I took 2 things in there, so let me call this, I'll just call this U for a second, right? So if I took, in what I want to call the space of functions, the notation I use is R. Okay, so maybe the set theory notation needs some explanation, but let's just take that as a definition for now. So I take f and g in that space, and that's a vector space, so I know it's a vector space. So I just need closure, right? I don't need to prove all 9 axioms. I need closure under addition, closure under multiplication, and 0, right? So is it true that 0 is periodic for p? 0, yeah, because it gives me 0 everywhere, right? So 0 is clearly p periodic in a silly way, right? And we're not, this isn't saying it's the smallest period, right? So it's not like when we think about trig, we usually think about the smallest period p, right? This has to hold for a p. That's all we're saying, right? So in the trig functions, this p could be 2 pi, for example, instead of just whatever the periodicity, well, 2 pi is, could be 4 pi, right? I guess 2 pi is the periodicity, so I want to be careful there. And now we want to show, right, that if we take the sum, it's in this periodic set, right? So I need to show, like, how would you write this? You need to show that f of x plus f plus g of x plus p, right, needs to be the same as f plus g of x, right? But now we unpack definitions. What does this symbol here mean? it means f of x plus p plus g of x plus p, right? And what do we know about f and g? Well, they're periodic, so this is f of x plus g of x, right? And now we unpack in this definition in the other direction. This is f plus g of x, right? And that's what we needed to show, right? Clearly scalar multiplication, I say clearly, but same thing, right? That's going to work, right? Now, okay, so this is a subspace, right? Now, all this talk about this subspace may make you think the other one is not a subspace, right? And what would the problem with the other one be? So the other one is different, right? It just says you look at the set of F such that there is some P in the reals, such that f of x plus p equals f of x. And I guess you must say in the reals minus 0, right? Otherwise, it's kind of trivial. If I allowed 0, then of course everything would be periodic, right? But now it's not fixed, right? It can change, right? So if I take two of these things now, right? So let's call this one W, right? Okay, so if I take an F and a G and W, right? Then what I get is I get like a P sub F and a P sub G that can be different, right? And I know that f of x plus pf is f of x. And I know f of x plus pg is f of x. Sorry, g of x, right? But now I'm in trouble, right? F plus g of x plus what, right? We just need something. We need something to put there, right? Should be f plus g of x.
Something is 0.
All right. So now we're kind of in trouble, right? Because we don't know what to put there. That doesn't mean there's nothing there, right? So if we're going to show this is not a vector space, we need to come up with an actual example. I mean, so what? And I mentioned this in one of your posts already. This is a plausibility argument that this will not be a vector space, right? This is not yet an argument that this is not a vector space, right? I see a problem that I need to look for here. Okay. So what kind of thing might have to happen in order for f of x? I mean, yeah, no, let's just do it like this. Suppose I had here. So what is this? This is, let's say S, right? I'm going to find some S, right? What sort of properties would S have to have? So I have f of x plus s plus g of x plus s. That would be f plus g of x plus s, right? And this is supposed to be f of x plus g of x. All right, that's what we're assuming. Okay, now what might happen here? It might be nice if f of x, let's just see what would have to happen for f of x plus s to equal f of x, and f of x plus s, or g of x plus s to equal g of x. What would have to happen for this to be the case? Well, okay, s could be 0, right? But that's probably not going to, again, zero is not allowed, right? We're not allowing 0. We need a non-zero, right? So what we could do is we could start using a little bit of algebra on this s. S can be written as some qf pf plus rf, where this is a remainder, right? So we're using like the division with remainder, even though we have reals, right? We're dividing sort of with remainder with reals. I want this to be an integer, right? I want this to be, because I want this to be some integer, right? Something like that, okay? So I'm taking s, I'm dividing by pf and getting the best integers I can put in those two places to get me back s, right? I'm not even sure, now I'm not completely sure about this argument, right? But I can do the same. Let's pretend this works. I'll leave it to you to see if it works or not. P of g plus r of g, right? I got something like that. Now I got to think about this. I believed it when I said it earlier, but maybe, okay, this is still a plausibility argument, but a slightly more plausible plausibility argument. And so what actually happens here? Well, so f of this thing here, you can see where I'm going with this. Q of f, p of f, sorry, let's try that again. F of x plus, so f of x plus s, right, is f of x plus qf pf plus rf, right, like that. Okay, but this is the same as f of x plus, well, this is a bunch of copies of pf, right? Actually, no, I just need this to be an integer. That's the only thing I need to be an integer. So this is fine. I'm saying how many times can pf go into s, an integer number of times. That's what I'm doing, right? And then there's some remainder. So that's fine. Even in the reals, that's fine, right? But because this has periodicity pf, this part can be thrown away, and I just get this rf here, right? Okay, and then same with g, right? G of x plus s, right, is going to be g of x plus rg, right, like that, right? So now if we also knew that these were the smallest periods for f and g, right, then because the remainder is less than those periods, right, maybe has absolute value less than those periods, so let's say smallest in absolute value, what do I know? I know that this can't be f of x, right, and this can't be g of x, right? So the only way this thing is going to work is if those two remainders are 0, right? And then what I'm getting from all of that is I'm basically getting that the ratio of p of f to p of g has to be irrational, right? These are integers, right? So in other words, I'm getting that qf pf has to equal, because this is s, right? Q g p g, right? So I'm getting the ratio of pf to gf to pg has to be qg over qf, but this is this is in the rationals, right? So what is the long story of that? In order for this to be periodic, right, the two periods p and g, for the function f and the function g, have to be in a rational ratio to each other, right? If you think about this, this comes up a lot in trig, right? It comes up a lot. Comes a lot in differential equations if you do Fourier series and stuff like that, right? There's only certain sort of combinations you can use. You need these rational combinations of the periods, right, in order for things to work out. Okay. So if one of my functions is period square root of 2 and the other one is period 1, for example, right? That's probably not going to give me a rational function. It's not going to give me a periodic function, right? So it gives you a place to look. Now you can now define a function based on sine x, where the period is square root of 2. How do you get the period? Period is usually 2 pi, right? So I want it to be square root of 2, right? So I want sine. Now I've got to remember my sort of ax. The period there would be 2 pi over a, right? So I would want this to be square root of 2, right? So I want a to be square root of 2 over 2 pi, right? So I'd have sine square root of 2 over 2 pi. And if I wanted my period to be 1, it'd just be sine, oh, and then x, right? Sine 1 over 2 pi x, right? So this would have period square root of 2, this would have period 1, right? And my claim from all this stuff we did is that sine, see, this turns into a real problem, right? I mean, it turns into a real just sort of math problem. This thing, and you can draw it, right? You can plot this and see what you get, is not periodic, right? So in other words, if I take sine, right, which are both periodic, and I sort of play with them so I get two different periods, which are not in a rational ratio to each other, right, then the resulting function is going to be non-periodic, right? That's already an interesting like trig question or something, right? So Yeah, so I mean, this problem had a lot to it. It was an interesting problem to work out all the way, right? So what is the upshot? Is that set they gave you a subspace or not? No, right? So the long-winded thing, yeah, so the answer is no, it's not a subspace. It's not closed under vector addition, right? It's perfectly well closed under scalar multiplication because you're just multiplying by a number, right? Because that only uses one function, right? So that's fine. Definitely has 0, that's fine, but it's not closed under scalar addition, or not closed under vector addition, right? So that's what I mean by the problems here are good, right? So these problems can make you think. I mean, once you do these problems, you should have a good feeling for what you're doing. Good, all right. Let's see, let me get a little bit into this stuff. Let me go to the notes I had. So these are the notes I was wanting to say something. Let's see, where do I have this? Yeah, okay, so independence we kind of already talked about, right? So when you're given some vectors in a vector space and you want to show they're independent, okay, usually what you need to do is you need to say, you suppose there's a combination. Right? So you suppose that's true, right? You need to show, so suppose that, right? You're going to show that A1 equals A2 equals all the way through AN equals 0, right? So that's what you need to do to show that V1 through Vn is an independent set of vectors. Okay, almost always that's what you're going to do. Okay, depending on your vector space, there may be lots of tools to do that, right? So if the vectors are coming from Fn, then that's where you get all the Gaussian elimination stuff, right? Because now these vectors, right? If these are elements of Fn, you know, then this V1 thing is really something. Let me say that we're in F3, right? Just to make it simpler. And let's say that I have some vectors here, I don't know, 1, 2, 3, 3, 2, 1, 2, 1, 3, right? And I want to show that they're linearly independent, right? Then what do I need to do? I'm going to do this, right? I'm going to say, suppose A1 times 1, 2, 3, A2 times 3, 2, 1, plus A3 times 2, 1, 3 equals 0, which in this case is the 0 vector, like that, right? Now this is interesting, right? Because this isn't right now a system of equations. This is another interesting aspect of the vector, you know, this matrix representation. This is a linear combination of 3 vectors in R3, right? And I'm asking, is this that, right? But I can rearrange this to look like this, right? I can rearrange this to say, well, what I really need here is I need A1 times 1, so 1 times A1, plus 3 times A2, plus, and I can't even remember what I have, 2 times A3, equals 0. And then I need 2 times A1 plus 2 times A2 plus 1 times A3 equals 0, right? And then this last one is 3 times A1 plus 1 times A2 plus 3 times A3 equals 0, right? So now we have exactly the same kind of question, but now instead of being a linear combination of vectors, it's now a sequence of 3 equations and 3 unknowns, right? So notice that this has some geometric content, right? This geometrically is describing the intersection of 3 planes, right? This is describing putting 3 vectors in R3 together, right? Completely different pictures, but it's asking the same question, right? And now what do you do? Well, you turn this into a matrix question.
You're finding the determinant equals 0.
And then there's lots of options, right? So one thing is a determinant, right? So when is this thing going to have only the 0 solution as a matrix? Now, those of you who haven't had linear algebra, you'll have to just buy whatever someone else says here. So the determinant needs to be 0 or not 0?
Needs to be 0.
So if it's 0, it means there's lots of solutions.
Needs not to be 0. Sorry, you're
It needs to be not 0, right? Is what it needs to be, right? So that's one option. You could take the determinant. The other thing you could do is you could do Gaussian elimination, right? And you could solve it, right? You could just solve this system and see that you have just 0, 0, 0 as a solution, right? So if you don't know what determinants are, and by the way, you can get through most of this class without knowing what determinants are, because the main thing this guy does is avoid determinants, right? And if you sort of read his philosophy, what he's doing is avoiding determinants. So he goes out of his way to not use determinants. Yeah, but I mean, you could use Gaussian elimination and solve this thing, right? There's various things you could do here, right? But just keep in mind, the basic step was write down a linear combination, set it equal to 0, and then do whatever you can do, right? That's sort of the next step, right? Okay. Anyway, that's typically how you show things are independent, okay? What does spanning mean? What does it mean to say these set of vectors span R3? What would that mean?
I could have this backwards, but I think it means that they cover, like if it spans something, it covers that entire set.
So we'd cover all of R3, right? Yeah. So
Yeah.
to say the span. So let me just call this V1, V2, and V3. So the span of V1, V2, V3, right, is R3. Just means if I take the set of all linear combinations, right? So the set of all summation AI VI I equal 1 to 3, where AI is in R, right? We're working over R, right? Set of all those things, right? By the way, that's just let me write that another way. That's supposed to be R3. If we're thinking about our subspace notation, right? I could say that this is just the vector space V1 multiplied by everything in R, right? What would that be? That would be a line in R3 in the direction of V1, right? Because I'm taking V1, I'm looking at all scalar multiples of V1, right? So if I take a vector and I look at all scalar multiples, I get a line through that vector, right? And then plus R V2, right? So it would be the line going through V2 plus R V3, right? So this sum up here is really the same as what we'd have as the sum of those 3 lines, right? Same idea, okay? Right? And is that the case here? Let me see. Is it the case that we get all of R3 here? Do I have to check? It would be pretty hard to check every single vector in R3 to make sure that I could solve for it, right? So what could I do here? This is chapter 2 stuff, but it's from further along. So we know these are independent. We know there's 3 of them. Right? Is there a basis for R3 of size 3? What's the standard basis for R3? Just 1, 0, 0, right? 0, 1, 0, 0, 0, 1. So it's very clear that anything in R3 can be written as a combination of those, right? And it's very clear that these are independent. Right? So this is a set of independent vectors that spans all of R3, right? So it's a basis, right? This is a set of independent vectors. There's 3 of them. So is it a basis? So this is the main thing in this chapter in some sense, right? Any basis has the same number of vectors for a vector space, right? So that's sort of a key thing. That's called the dimension of the vector space. And generally we're working with finite dimensional vector spaces. To say it for infinite dimensional vector spaces and prove it for infinite dimensional vector spaces requires some extra tools from set theory, right? So we're going to sort of avoid that situation. everything is true for infinite dimensional vector spaces, but we're just dealing with finite dimensional vector spaces when we're talking about this kind of thing. Okay. I mean, we do have an infinite dimensional vector space that we use. We use as PF, right? That's the set of all polynomials, right? What's the basis? What's an easy spanning set for this polynomial? For the set of all these polynomials. So if I just take 1, x squared, etc., right? All of those. So what is the span of that? What's the set of all summation? AI x to the I equals, 0 to n, for AI in F. It's just is the set of polynomials, right? So the set of polynomials just is the span of this set, right? The space PMF is the span. Now this is a finite dimensional one. You only go up to the m-dimensional stuff, right? Okay. But this is an infinite dimensional set, and this is a basis for that infinite dimensional set. It is a spanning set. It's independent, right? So we do have some infinite dimensional basis sitting around that we occasionally look at. Okay. So let me just write down the most important things. Okay, let me just write down the most important things. So if we have, so here's the important theorems from this section. So 1, if V equals span of S, V is a vector space, right, over some field F, right? So if V is equal to span of S, then there exists some S naught subset of S, such that S naught, such that V equals span of S naught, and S naught is, I'm just going to say independent instead of linearly independent. Okay. So what this theorem says is we can take any spanning set and shrink it to a basis. Okay, so that's a very important theorem. In the case for infinite dimensions, it takes some extra work, but the case for finite dimensions is what your book deals with, right? And so if we have a finite spanning set, finite thing here, right? Then what can I do? I can just show that I can throw away stuff, right? So let's just actually look at how the argument works. I want to, so suppose S is finite. So let's add that assumption, right? Then, okay, if this is not linearly independent, it's interesting, lots of other interesting math comes along the way. If S is not linearly independent, sorry, let me just write not independent. Just write not end, okay? What do I know? Remember, what does it mean to be independent? It means I can add the things together, right?
So
and get 0. Yeah, go ahead.
So if it's not independent, that means that the vectors must be 0.
No.
No, I'm sorry.
The linear combination is not 0.
It's not 0.
No, it means I can find a linear combination. It's non-trivial. That is 0, right? That's what independent means. Sorry, if it's not independent, right? We're looking at the not independent case. If it's independent, we're done, right? Our S works, right? If it's not independent, then I can find some vectors in there which are 0, right? Where all of these AIs are not 0. I don't even need to include the 0 ones. I just take the non-zero ones, right? That's what it means for S to be not independent, right? I can write 0 as a non-trivial linear combination of vectors in S, right? But then what can I do? Well, then I can rearrange this and say A1 S1 equals minus A2 S2 plus dot 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 plus AK SK, right? And then what I can do, because we're in a field, right? This doesn't work in the integers, for example. We can't look at vector spaces over Z because of the step I'm going to do next, right? So I can say S1 is equal to 1 to minus 1 over A1, because I need to be able to divide, right? And then this stuff here, right? A2 S2 plus dot 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 plus AK SK. Right? So in other words, S1 is in the span of S take away S1. Right? So what does that mean? I can throw away S1 and I get S1 back. Right? So what is the span of S minus S1? Well, it's got everything except S1, but it also has S1, right? So it's actually the same as span S. But that was all of V, right? So what have I done? I've taken my set that spans and I've thrown away one vector and it still spans, right? So now what can I do? I can say let S naught be a subset of S of smallest size. This is where we're using finite, by the way. So that it still spans. How do I know I can
S
get?
naught is essentially after you've thrown out all the stuff and you're still able to span the whole thing.
Yeah, I mean, but in this case, we're in a case where I don't know how many things there are. I just know it's finite, right? So I just throw something out. I got a new set. I got to throw something out. So one way would be to do induction, right? Okay, but induction is equivalent to something called the least member principle, right? So what I can do is I can look at finite subsets, right? And I can find the integer, right, which is smallest, so that there's a subset of size S naught that spans V, right? So I mean, formally, I'm saying look at the set of all M, such that M is the size of a set S naught. S naught is a subset of S, right? And the span of S naught equals the span of S. It's called a set A, right? So is 0 in A? So 0 is not an element of A. I can't span V with nothing, right? So that can't happen, right? So these are all positive integers, right? This is a non-empty set. And if I have a non-empty subset of positive integers, there's a least one, there's a minimal one, right? That's the least member principle. And that's equivalent to induction, right? So we're actually using something here, right? So if I take the smallest possible M and I take a subset of smallest possible size, then I can't throw one away, right? So it must be independent. See what I mean? So it's like you're choosing a least example, right? Like that. Okay, so that's where we're using finiteness. We're using finiteness to find the smallest thing that I can use here. If we didn't know that we're in a finite dimensional thing, I couldn't use this, right? Because these may all be infinite sets. If I throw one thing away from an infinite set, it's still infinite, right? I haven't gained anything in that sense, right? So your argument has to be different there, right? Okay, but basically the idea is you throw things away till you're done, till you get something that's linearly independent, right? On the other side, if I take, So that's, you can take a spanning set and shrink it to an independent set, right? I can take an independent set. Can I blow it up to a spanning set? And now the proof the book has is a nice one. I know, and again, this is where I'm finite dimensional, right? So V is finite dimensional. So I know that V equals span of some finite number of vectors. I've got some U1 through UK, which are independent. Right? And what I want to do is I want to extend this to a spanning set. Sorry, yeah, to a spanning set, right? I don't know it's spanning yet. I want to extend this to a spanning set. I know it's linearly independent. I want to extend it to a spanning set, right? So now what can I do, right? Same sort of thing. I mean, I know that U1, right, is in the span of V1 through Vn, right? Okay. So I can do a similar thing, right? I can say, well, U1 is equal to A1 V1 plus AN Vn, right? And then I can, and let's just, and you know, these can't all be 0, right? So here I've got this entire list. So I'm just putting here, some of these may be 0, some of them not. Let's just suppose A1 is not 0, for example, right? They can't all be 0, this would be 0, right? And 0 cannot be in an independent set, right? If 0 is in the set, definitely you have a linear combination, right? If 0 is in S, right, then 1 times 0 is equal to 0. That's a linear combination of things in S, which is giving me 0, right? So 0 cannot be in an independent set. That's a good thing to keep in mind, right? But what can I do? I can sort of flip these around, right? I can say, fine, minus or A1 V1 is equal to U1 minus all the rest of this stuff. AI VI. Right, and then I can do the same sort of thing I did before. I can divide by A1, right? So V1 is equal to 1 over A1. And again, we're using the fact that we got a field here, right? You know, and then U1 minus that stuff. Right, so what do I have is I have V1 is in the span of what U1 together with well, these things up here take away V1. All right, like that. And so I've basically swapped, right? Something in V1 for something in U1. Okay, and you keep going, right? So maybe this one's by induction if you like, right? So then you swap out U2, right? And when you swap out U2, you have to show that you have to be able to leave U1 over there, right? So when I do the next step, I need to show that, you know, I write U2 as a linear combination of these things, right? Well, the part that, you know, it can't just be a linear combination of U1 because these, you know, the UIs are already linearly independent, right? So like in the next step, U2 is a combination of these things, A1 U1 plus some A2 V2 plus dot 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 plus A N Vn, right? Okay, well this may or may not be 0 here, but one of these things has to have a non-zero coefficient, right? Otherwise U2 would be in the span of U1, and that we're assuming that's not the case. Right, so now I do the same sort of trick, say it's V2 and I swap out V2, right? You just keep doing that, right? So that's how that works, right? So you should read the proof in the book too, right? But that's basically how it works, okay? So what do? We can take a spanning set, we can shrink it to a basis, or an independent set, we can take an independent set, expand it to a spanning set, right? And the last thing is that any two of those things have to have the same size, right? So a basis is a independent spanning set, right? And a theorem is that every independent spanning set, every basis has the same size, right? And basically this proof is showing that too, right? If I take V1 through Vk, and I take U1 through Un, right? And let's suppose just that N is, say, bigger than K, right? I can do the same argument I just did and sort of swap out these VIs over on this side. And I can't end up with anything left over, right? Because once I get all the VIs stuck into that set, but I sort of replace one at a time, right? Then I have to run out at exactly the same time. We're late, so I'm sort of doing that little hand wavy, right? But that's the idea. Those are the main theorems, right, in this section. A finite dimensional vector space, the dimension of that vector space is determined by any basis, right? And we use that above a little bit, right? I mean, we used it up here when we were doing this. Oh, that far back, right? We have this basis of size 3, right? This is an independent set of size 3, right? So that's a basis, and it necessarily spans, right? So we're using that theorem there to sort of do that sort of stuff. Okay, a lot. If you want to see more problems done, you just have to ask for them, right? Just like we stopped and did that problem. You know, I'm always willing to, we could just, like, if you have plenty of problems to work on, we could just work problems, right? So that part is kind of under your control. If you don't ask for problems, I can talk forever. I mean, Austin knows I can talk forever, even though my voice will go away, right? Okay, I will post this video, and I will post these notes if they do you any good, right? Maybe they do, maybe they don't. And I will also post this link, a link to this little page I have over here where I had the notes I wanted to get through. And then I have some notes from 345 on systems, and I have some notes on the CR decomposition. If you want to look at those, the sheet we gave you is pretty good too. The little ode to Gaussian decomposition, whatever that is, that's a good explanation too. So you don't have to look at these. You can just look at that, right? Any other last minute questions? Maybe we were going to look at the MATLAB thing if you feel like still hanging out.